Hello students, welcome back. Let us resume our discussion in section 1. The next topic, let's talk about 1.4, block cipher. And block cipher is a simple example of transposition cipher, which is an unfortunate name. It should have been called permutation cipher, but for some historical reason it was named that way. Unfortunately, it's too late to change. It depends upon what kind of permutation we have. So any 1 through m, and we have appropriate change of word. So basically what we are looking at is a 1-to-1 onto map from a set 1 through m to the same set 1 through m. So basically we permute those, and then if you know what map it is, then we can take the inverse map to unscramble and bring it back. And what kind of permutation are we looking at? Well, hopefully something we can easily remember and easily calculate. So for simplicity, the person who proposed for the first time, Lester Hill, proposed a linear map, an invertible linear map. What am I talking about? Let's see. We have plain text message and then divide it into m letter blocks. So first character P1, second character P2 up to mth character, and then assign appropriate coefficient like this to form a matrix. So C, crypted letters, m block is C, and plain text is P. So we have matrix multiplication. And then in order to have that P back from C, we have to have an inverse matrix. So we have to have this condition, but I don't want to go too deeply into this matrices and inverse matrices for higher dimension. Not everybody took linear algebra here. So let's keep it simple. Here's an example, and let's keep it to just 2 by 2. So this much I think most people were exposed through pre-calculus. Here's an example. Let's keep 2 by 2. If you have larger matrix, m by m matrix, then basically we are looking at more complicated key structure, so more secure. But the trade-off, of course, is more complicated. So let's keep it simple, just 2 by 2 matrix. And here's an example: 2, 3, 5, 8. And then its inverse matrix turns out to be -8, -3, -5, 2. Here I use, maybe would have been a bit easier. -5C2 plus 2C2 like that. Maybe this would have looked better. Or maybe not, I don't know. Anyway, here is the inverse matrix computation. Remember this? 1 over AD minus BC, and that turns out to be 1 here. So AD minus BC is 1. 2 times 8 is 16. 3 times 5 is 15. So I don't really have to worry about this. And that probably is by design to make the computation simpler. And then switch the principal diagonal. 8 and 2, switch those. And then the other diagonal, we take negatives. So that's the inverse matrix, and that'll give me the inverse map. And you can check easily, multiply these two matrices, and then you get the identity matrix back. Okay, keep that in your mind, and let's apply this to a certain message like this. By now, okay, we are doing 2 by 2. So let's take 2 letter blocks, 0, 1, 2, 0, and then 24 and 13, there's a space, but join those two, and then 14, 22 like that. So first block, and then the second block, 2 letter blocks, and then the third block like that. Make sense? Okay, and then here we're going to apply this encryption map. How does it work? Let me show you. Let's see. C1 is 2 times P1 plus 3 times P2. So P1 is 1 and P2 is 20. Put those, we get 10. And then likewise, 5 P1 plus 8 P2. Calculate, we get 0.9, and that's the result. 10, 9, and then that'll give me first two sentences, KJ. Alright, so by now, BU became KJ. I don't want to get italic here. And then next two letters, green, 24 and 13, put those in, same map here, and then we end up with 9 and 16 respectively. So that's gonna give me JQ. And then here's a third computation. Again, the same map, the encryption map. And then put P1 as 16, P2 as 12, and do your computation. Oh, excuse me. P1 as 14 and P2 as 22, and do your computation. Brown, and then that's going to give you QM. So by now here, okay, all right. And then if you want to decrypt it, then you can apply the inverse map, the decryption map. And that comes from inverse matrix, as a matter of fact. But if you're not too comfortable with inverse matrices, let's not worry too much about that. So I de-emphasize that computation in gray. But if you go ahead and calculate that, put those into the inverse matrix and do your computation, or if you're not comfortable, put that into this inverse map there and then run your computation, you're gonna get the original message back, 0120, so BU, and then 24 and 13 YN, and then 14 and 12 ONW, so we get the original message back. And interesting thing is, let's see, we have JJ and QQ down here, but they didn't come from the same information, right? So this too is actually polyalphabetic. So it's hard to break using statistical analysis. And then as for the key, well, that's the key. The matrix 2358, that's the key. And then from here, this 2, 3, I'm highlighting those coefficients in red. That's the encryption key. This matrix. And then for decryption, well, we find that inverse matrix turns out to be this is the decryption key. 8, -3, -5, 2. So there goes an example of block cipher, especially linear block cipher. Nonlinear block cipher, of course, is more complicated. Here's a summary basically. A crypto system is basically a 5-tuple. The P is a class of plain text strings. C is a class of ciphered strings. So P, plain text, so text you can read. C, scrambled sequence of alphabets, so you cannot read. K is the keys, basically. And then E is the class of encryption functions. In some cases, we have just one function, but in some other cases, we use multiple functions. Again, for the keys, sometimes we use just one set of keys all the time, but in some other cases, we use a little bit more complicated key system. The more complexity we add, the more secure we get, but at the same time, the more inconvenient it gets. And as for getting inconvenient with all those frequent changes of passwords and having a lot of difficulty finding those, and then if you list those in your and print out and then attach it to your wall, then that's a big no-no, those kind of things. And sometimes people use some software to automatically generate those passwords, but then again, if you lose that information, then everything is lost. So we have all those trade-offs associated to those. Anyway, those were classical examples, and from the next video, let's talk a little bit more about modern examples.